Physics enters a peculiar realm the moment the universe begins to oscillate. Here, we will journey together into the world of gravitational waves, which are essentially tremors in space-time generated by violent celestial events. Until not long ago, these ripples were purely theoretical. But now, we can actually detect their presence, and every signal we receive unveils a cosmos we never realized was there. To grasp this concept, you can picture the universe as an immense ocean, with stars and planets adrift on its surface like vessels. When two of these massive bodies collide, they produce waves that propagate through this cosmic sea. These are gravitational waves, and they race through space at the speed of light, carrying with them a wealth of information about the powerful events that created them. Their significance to us is profound, as they provide a deeper understanding of the reality we inhabit. For most of human history, astronomers were limited to observing the cosmos solely through the light that stars radiate. Gravitational waves, however, present an entirely new method for perceiving the universe. By capturing these waves, scientists can access data on phenomena that would otherwise be completely invisible to us. In effect, this has granted us an additional sense, expanding our ability to perceive the cosmos around us. To truly appreciate this, you need to understand the theoretical foundation of gravitational waves, which originates with Albert Einstein's theory of general relativity. His theory posits that gravity isn't a simple force, but rather a warping of space-time itself, caused by the presence of mass. When colossal objects like black holes interact, their immense gravity distorts this fabric, sending out the very ripples that travel across the universe. But proving these waves existed was an immense challenge. Detecting them is an incredibly difficult undertaking, akin to trying to discern the sound of a single leaf falling during a raging thunderstorm. The instruments needed to capture these signals must be extraordinarily advanced and sensitive, as scientists had to engineer tools that could measure shifts in space smaller than the diameter of a single atom. This quest led to the creation of the Laser Interferometer Gravitational Wave Observatory, or LIGO, which has been central to this entire field of study. The observatory, with facilities at 2 separate sites in the United States, was constructed specifically to register these infinitesimal vibrations in space-time. It operates using an elegant system of lasers and mirrors that can measure the minute distortions that occur when these waves wash over the Earth, with each detection marking a new milestone in astronomical history. With this technology, gravitational waves were proven to be more than just a theoretical curiosity. In 2015, LIGO achieved the first-ever confirmed detection of these waves, which originated from the merger of 2 black holes. This singular event not only validated Einstein's century-old theory, but also ushered in a revolutionary new era for astronomy, allowing scientists to map cosmic events in ways that were previously impossible. These waves do not just tell us about the existence of extreme cosmic events. They are also carriers of immense energy. For instance, when 2 black holes coalesce, they unleash a tremendous burst of energy in the form of gravitational waves. This energy, much like sound, radiates through space, providing vital clues about the cataclysms that took place in the farthest reaches of the universe. However, the merging of black holes is only one type of event that produces these space-time ripples. Spectacular stellar explosions, known as supernovae, also leave their distinct signatures on the cosmic fabric. International collaboration between observatories like LIGO and Virgo has been indispensable in capturing these events, forming a network that greatly enhances our ability to survey the cosmos and its dynamic, ever-changing nature. As our research advances, we've learned that these waves possess different frequencies, much like sound waves have varying pitches. The specific frequency of a gravitational wave depends on the cosmic event that produced it, and these variations contain key information about the source's origin and characteristics. It's as if we are learning to hear the universe in a symphony of different tones and melodies. This newfound ability has given rise to a field known as multi-messenger astronomy, where we combine data from gravitational waves with information from other forms of radiation. This comprehensive approach allows scientists to get a more complete understanding by using gravitational waves, visible light, gamma rays, and other cosmic signals to paint a far clearer picture of what is happening out in space. One of the most pivotal moments in this new field was the event known as GW1 70817, which was the first time we detected the collision of two neutron stars. This observation was monumental because it was not only registered as a gravitational wave, but was also seen across the entire electromagnetic spectrum, from visible light to gamma rays. This breakthrough fundamentally altered our approach to studying cosmic events and their connection to the formation of heavy elements in the universe. The future of gravitational wave astronomy appears incredibly bright and is filled with limitless potential. As our technology continues to improve, we will gain the ability to detect signals from more distant and fainter sources, which will permit us to probe even more deeply into the universe's greatest mysteries. What incredible discoveries await us in the decades to come is a question that only time can answer. As we continue to explore this fascinating realm, it's crucial to recognize that every new discovery brings us a step closer to solving the fundamental puzzles of our universe. These gravitational waves are far more than mere vibrations. They are cosmic messages, beckoning us to listen carefully and learn from the extraordinary wonders that surround us. The stories they have yet to tell are only just beginning to reach us. Instead of ripples on water, imagine waves in the very fabric of space and time. These are disturbances triggered by some of the most extreme events in the cosmos, such as the collision of black holes or the explosion of supernovas. To grasp what they are and how they form, you need to venture a bit deeper into the universe. When two colossal objects, such as black holes, are locked in a mutual orbit, they engage in a sort of cosmic ballet that distorts the space around them. As these celestial bodies spiral closer to one another, their gravitational pull intensifies, profoundly warping the surrounding space. This dynamic movement doesn't just affect the black holes. It also radiates waves that travel at the speed of light, propagating throughout the cosmos. You can picture it as the vibrations from a colossal cosmic drum, echoing through the vast emptiness of space, which raises the crucial question: can you actually detect these cosmic ripples? Attempting to sense gravitational waves is much like trying to hear a single whisper in the middle of a raging hurricane. Their signals are incredibly faint and demand highly advanced technology for any hope of measurement. Despite their profound weakness, by the time they arrive at Earth, their discovery provides us with a way to look beyond the limits of conventional telescopes and witness the universe in an entirely new light. The very existence of these waves is fundamentally tied to Albert Einstein's theory of general relativity, which redefines gravity not as a simple force, but as a curvature in space-time itself. Picture a trampoline where the stretched surface is space-time. Heavy objects like planets and stars act like bowling balls, causing the fabric to bend. As these cosmic bowling balls move, the shifting curvature sends out waves, and that is the fundamental nature of gravitational waves. Remarkably, these cosmic ripples do more than just signal that an event occurred. They offer detailed clues about the behavior of the massive objects that created them. For instance, by analyzing the specific pattern of waves from merging black holes, Scientists can deduce their masses and understand the intricate details of their interaction. It is truly astonishing to think that you can effectively listen to the universe in this profound manner. Gravitational waves also grant you access to eras of the universe that were once completely hidden from view. While light can be obstructed by immense clouds of cosmic dust and gas, these waves pass through such barriers unimpeded. This capability means you can now gather information about events that took place billions of years ago, which would otherwise be forever lost in the dark expanse of space. The relationship between these waves and cosmic energy is particularly fascinating. When two black holes finally merge, they unleash a tremendous burst of energy as gravitational waves that surge through the cosmos. This phenomenon not only showcases the sheer power of these cosmic events, but also leads to deeper questions about how energy is distributed and transported across the universe on the grandest scales. To measure these phenomena, scientists have developed instruments of extraordinary sensitivity. Observatories like the Laser Interferometer Gravitational Wave Observatory, or LIGO, are meticulously engineered to pick up on these minute vibrations. The way they distinguish these signals from background noise is through incredible precision, capable of detecting changes in distance smaller than the diameter of a single proton, ensuring the data is reliable. Moreover, gravitational waves give you the ability to explore the cosmos in a completely new dimension by integrating their data with other forms of observation, like visible light and gamma rays. This combined approach, known as multi-messenger astronomy, is poised to completely transform our comprehension of the universe. In essence, these waves are a captivating and complex phenomenon that enables you to learn about the most violent and extreme cosmic events. They unlock new avenues for inquiry and discovery, compelling you to understand the cosmos in ways you previously couldn't have imagined. What other secrets might the universe reveal through these cosmic vibrations? The quest has only just started, and every new detection brings you a step closer to a future brimming with possibilities. Einstein's theory of relativity revolutionized your understanding of the universe, presenting ideas that sound like they've been pulled from science fiction. At its heart, general relativity reveals that gravity is not merely a force that pulls objects together, as was previously believed. Einstein instead theorized that gravity is the consequence of the curvature of spacetime, the very fabric that constitutes the universe. Imagine spacetime as a vast, taut rubber sheet. When you put a heavy object on it, like a star, it creates a dip. A smaller marble rolled nearby won't travel in a straight line, but will follow the curve created by the heavier object, which is how gravity operates. But what unfolds during cataclysmic cosmic events, like the merger of two black holes? In those moments, the curvature of spacetime doesn't just get deeper, it propagates across the universe as waves, much like the ripples that spread when you toss a stone into a pond. The collision of two black holes generates a kind of earthquake in the structure of spacetime itself, and these resulting waves travel at the speed of light, carrying information about their violent origin. It's astounding to consider that even though these waves are exceptionally faint, they can journey across the entire cosmos, passing through planets and stars without being altered. Can you imagine something so delicate carrying messages about such powerful events? Yet to capture and interpret these waves, you require technology of unbelievable sophistication, as their presence is almost imperceptible. Relativity not only clarifies how these waves are born, but also gives you a framework for studying the universe and predicting the behavior of celestial bodies. For many decades, scientists have been hunting for proof of gravitational waves. The fundamental issue is that these waves are significantly fainter than any other known form of radiation, like light. So how can researchers be certain they are real? This is where Albert Einstein's theory serves as an indispensable guide, as his predictions about the behavior of these waves have shaped the very design of the experiments and observatories dedicated to finding them. Some of these experimental efforts led directly to the creation of observatories such as LIGO, the Laser Interferometer Gravitational Wave Observatory, which was built for the express purpose of detecting these cosmic ripples. The facility operates with a massive L-shaped tunnel through which a laser beam is projected. When a gravitational wave passes by, it warps the fabric of spacetime itself, which in turn alters the lengths of the tunnel's arms. These changes are infinitesimally small, yet the detectors possess such extraordinary sensitivity that they can register shifts smaller than the width of a proton. Gravitational waves stand out as one of the universe's most captivating phenomena, but their detection has presented a colossal challenge to the scientific community. To grasp why capturing these cosmic travelers is so difficult, you must first understand their basic mechanics. They are often compared to the ripples spreading across a lake after you toss in a stone, where the stone represents a cataclysmic event like two black holes merging. However, these waves are incredibly faint and far harder to measure than any ripples on water. When a star explodes or a pair of black holes collide, they generate a disturbance in the very structure of spacetime. These tremors are so subtle that they are nearly impossible to perceive, even with our most sophisticated instruments. Think of trying to discern a single quiet melody amid the overwhelming noise of a massive concert. This illustrates the difficulty scientists face in isolating these waves from the universe's background static. Can you imagine the focus required to pick out that one tune? The primary obstacle stems from the unbelievably small scale of the distortions that gravitational waves produce. As they ripple through our planet, they might change the distance between two objects by an amount less than the thickness of a single human hair, demanding that our detection instruments be built with unprecedented sensitivity. The solution to this challenge lies in groundbreaking technologies, particularly interferometers, which use a precise system of lasers and mirrors to measure the slightest variations in space. However, technology isn't the only hurdle. External interference poses a constant threat of false positives. Everyday vibrations from traffic, seismic shifts in the Earth, or other environmental noise can easily create signals that mimic the signature of a gravitational wave. To overcome this, scientists must meticulously separate the authentic cosmic signal from all the background chatter. This is often achieved through global collaboration, where data from multiple observatories is cross-referenced to confirm a genuine event. The journey from the theory of relativity to the successful detection of these waves is a powerful story of human curiosity and our relentless drive to comprehend the cosmos. After many years of dedicated work, the LIGO team achieved a breakthrough in 2015, making the first confirmed detection of gravitational waves. This discovery was like finally hearing a beautiful song that had been playing silently for eons, and it heralded a completely new era in the field of astronomy. With this new capability, scientists can now observe cosmic events that were once entirely invisible, gathering information not just about the waves themselves, but also about their violent origins. It's as though you have been granted an entirely new sense for exploring the universe, one that allows astronomers to perceive what optical telescopes could never show. This enables the study of events that occurred billions of light years away, allowing us to receive messages from the distant past. Every time a new gravitational wave is detected, it's like receiving an echo from an explosion that happened billions of years ago, offering fresh clues about the fundamental nature of our universe. Through these waves, we can investigate the formation and evolution of black holes and trace the intricate dynamics of galaxies. Each new discovery not only validates Einstein's profound vision, but also unlocks a new set of questions, pushing the boundaries of what we thought was possible. General relativity remains one of the most elegant and impactful theories in all of modern physics. Every detected gravitational wave provides a direct glimpse into a cosmic event, telling a story about the universe in its purest form. By understanding this theory, you not only approach the answers to how the cosmos operates, but also venture into the unknown, where every solution reveals even deeper mysteries. Einstein's theory, therefore, is not just a collection of equations, but a master key that unlocks a universe brimming with wonders, calling you to become an explorer and to seek knowledge beyond the stars. In a way, you can think of gravitational waves as an entirely new kind of telescope, one that perceives the cosmos not through light, but by listening to its fundamental vibrations. This naturally leads to a compelling question. What other cosmic enigmas might this emerging field of astronomy help us solve? As our technology becomes more sophisticated, so will our capacity for detecting and interpreting these waves, making continued investment in this research absolutely essential. The next generation of observatories is poised to be far more sensitive, empowering us to capture signals from fainter and more remote cosmic events. With every new observation, we inch closer to resolving some of the most profound questions about the universe and our own existence within it. So, the next time your thoughts turn to the cosmos, I encourage you to remember the silent symphony that constantly unfolds. The melody of gravitational waves, which carries tales of creation and destruction across the immense expanse of space. Each discovery represents another stride toward comprehending the true nature of space and time, a pursuit that has captivated human curiosity for ages. Just consider what incredible revelations might be waiting for us on the horizon of this new astronomical frontier. Within this vast and mysterious universe, there is a remarkable feat of engineering that has utterly transformed our cosmic perspective: the LIGO Observatory. This scientific titan is much more than just a facility. It serves as a gateway to a new realm of discovery, enabling us to perceive the echoes of cataclysmic events from the distant past. So, what exactly is LIGO, and what makes it so vital to the field of astronomy? LIGO, an acronym for the Laser Interferometer Gravitational Wave Observatory, was constructed with one singular mission: to register the passing of gravitational waves. To understand how it operates, you can picture spacetime as the surface of an enormous, placid lake. When a stone is cast into the water, ripples spread outward. Similarly, gravitational waves are disturbances created by colossal cosmic occurrences, such as the collision of two black holes. LIGO is meticulously engineered to sense these almost infinitesimal ripples as they cause minuscule distortions in spacetime. The immediate question is how any instrument could possibly measure a phenomenon so subtle. The key is its astonishing precision, which allows it to identify changes smaller than the width of a single proton. To pull off this incredible feat, LIGO employs a system based on laser interferometry. Imagine a laser beam that is split and sent down two perpendicular arms, each extending for several kilometers. As a gravitational wave passes, it subtly warps the fabric of space, causing one arm to lengthen fractionally while the other simultaneously shortens. By precisely comparing the travel time of the light along both paths, scientists can confirm the presence of a gravitational wave. The observatory's significance, however, extends far beyond its detection capabilities, as it has truly inaugurated a new age in astronomy. Before LIGO's existence, our knowledge of the universe was built almost exclusively on observations of visible light and other forms of electromagnetic radiation. Yet LIGO has demonstrated an entirely new method for sensing the cosmos. For you, this means we now have the ability to investigate cosmic events that were previously completely hidden from view. One of the most monumental moments in the observatory's history came in 2015, with the first ever direct detection of a gravitational wave. That event was a powerful confirmation of Einstein's theories and the official birth of gravitational wave astronomy, adding a fresh, powerful instrument to our cosmic orchestra. LIGO has given us a way to hear the universe in a manner we never imagined was achievable. But what does the process of detecting these waves truly involve? Think of it this way. Each time two black holes merge, they create a kind of thunderclap that reverberates through the fabric of spacetime. LIGO functions as an incredibly sensitive microphone, capturing these cosmic disturbances. Every signal that is detected contributes a new piece to the universal puzzle, offering insights into the fundamental properties of black holes and their dynamics. As LIGO carries on with its mission, it works in concert with other observatories like Virgo in Europe to form a global detection network. This collaboration allows researchers to triangulate the source of an event in the sky, much like a group of people can pinpoint the origin of a sound by using their different positions as reference points. The more observations we collect, the more detailed our picture of the universe becomes, and the more questions we are equipped to answer. It also has the capacity to detect gravitational waves from less violent sources, such as the merging of neutron stars. This capability opens up entirely new avenues of research, enabling us to examine how these occurrences contribute to the cosmic synthesis of heavy elements like gold and platinum. The international collaboration that supports LIGO is another one of its remarkable features, with scientists across the globe working together to analyze data and validate discoveries. This spirit of cooperation not only speeds up the pace of scientific breakthroughs, but also brings the world community together in a shared pursuit of knowledge. Every discovery is a collective triumph, serving as a powerful reminder that human curiosity is boundless. Ultimately, the LIGO story stands as a powerful testament to human ingenuity and our unyielding desire to understand. Every time a new gravitational wave is registered, we move a little bit closer to unraveling the deepest secrets of the cosmos. These waves are more than just an interesting phenomenon. They are a vital tool that allows us to explore the universe in its totality. Looking ahead, it is truly exciting to contemplate what LIGO and its counterparts will reveal next. With every technological upgrade and each new detection, a universe of possibilities unfolds, prompting us to ask, what other secrets does the cosmos hold? The answer is out there, and LIGO is our greatest instrument for finding it. Whenever an object with immense mass moves, it warps the surrounding space, generating ripples that propagate throughout the cosmos. Cataclysmic celestial events, like the collision of two black holes, unleash these gravitational waves, which then travel at the speed of light. You can visualize this by thinking about a car crash. The force of the collision sends shock waves through the air. A similar phenomenon occurs in the universe, except these waves move not through air, but through the very fabric of spacetime itself. Despite traveling at such an incredible velocity, the effects of these waves are extraordinarily faint by the time they reach our planet. To understand how they influence the space they travel through, picture yourself holding a sheet of paper when the table it's on gets bumped. The paper will flex and warp, even while you are holding it steady. Gravitational waves have a comparable effect on space, causing it to subtly compress and expand along their path in ways we typically never perceive. So, what makes detecting these waves such a formidable challenge? Although they originate from the most powerful events in the cosmos and move at light speed, their impact on Earth is almost infinitesimally small. To give you a sense of scale, a passing gravitational wave might alter the distance between 2 points by a measure smaller than the diameter of a single human hair. You can imagine the monumental difficulty of measuring such a minuscule change using any conventional instrument. Detecting these ripples requires technology of extraordinary precision, which is precisely why the Laser Interferometer Gravitational Wave Observatory, or LIGO, was created. This project functions as a kind of colossal microphone, engineered to pick up on the faintest whispers from the universe. Through its groundbreaking technology, LIGO is capable of registering these minute fluctuations in spacetime. It achieves this by using lasers that travel down 2 perpendicular arms, forming an L shape, to measure distances with near-atomic accuracy. When a gravitational wave passes through, these arms stretch and compress slightly, a change that allows scientists to confirm its presence. It is truly remarkable to consider that space-time itself can be physically altered by these cosmic occurrences. Each gravitational wave that sweeps past us leaves its imprint on the universe's fabric, and this has profound implications for us. The ability to detect these waves opens up an entirely new way of gathering information, enabling you to observe phenomena that were previously invisible and shedding light on events that traditional telescopes could never capture. Beyond their fascinating nature, gravitational waves are also carriers of immense energy. To grasp this, think about dropping a stone into a pond. The ripples it creates carry energy across the water's surface. Now, imagine space-time as the pond and cataclysmic events as the stone. When 2 massive bodies like black holes spiral together and merge, the energy they unleash is colossal, and a portion of it is converted into these gravitational waves that ripple outward across the cosmos. This process transforms raw cosmic energy into waves that tell a detailed story. The specific characteristics of these waves reveal information about their source, including the mass and spin of the colliding black holes. Scientists act as detectives, decoding these messages to understand the exotic phenomena that created them. By combining data from observatories like LIGO and Virgo, we form an observational network that provides an entirely new perspective on the universe, with each detection adding a new chapter to our astrophysical knowledge. Different types of cosmic events generate gravitational waves at different frequencies, each with a unique signature. Just as a composer uses various notes to construct a symphony, astronomers analyze this spectrum of frequencies to piece together the history of the universe. By studying the distinct signatures of each event, you can gain deeper insights into how the cosmos has evolved over billions of years. The integration of gravitational wave astronomy with observations of other forms of radiation, such as light, is creating a revolution in the field. This approach, known as multi-messenger astronomy, allows you to view cosmic events from multiple perspectives at once. It's like assembling a complex puzzle. Each new piece of observational data, whether from light or gravity, helps to complete the overall picture and provides a far more thorough understanding of what occurred. Ultimately, comprehending how gravitational waves influence space is far more than a simple academic pursuit. It offers you a new lens through which to see your place in the universe. Every time we detect the echo of a distant cosmic event, we are reminded that we belong to something vastly larger, an immense ocean of energy and motion. Each wave tells a story of creation and destruction, of the birth of stars and the death of worlds, connecting us directly to the fundamental workings of the cosmos. Much like sound waves move through the air, gravitational waves transmit information about where they came from. When black holes merge, the energy carried by these waves offers insights into the mass and speed of the objects involved. You might wonder why understanding this energy is so critical, and the reason is straightforward. It deepens our comprehension of cosmic events and their effects on the cosmos. With every gravitational wave we detect, we are essentially receiving a message from space, a transmission brimming with energy that unveils secrets about the universe's past and present. Consider gravitational waves to be like road signs for a traveler. Every sign provides distinct information that helps you figure out which direction to go. In a similar way, these cosmic ripples do more than just signal that a massive event has occurred in space. They also tell us the story of how it unfolded. The energy these waves possess acts as a kind of map, guiding us towards some of the most spectacular phenomena in all of nature. However, there's a fascinating challenge we must confront. The energy of gravitational waves is astoundingly faint. It is not something you can perceive directly, contrary to what you might expect. Unlike the immediate sight or sound of an explosion, these waves demand highly sophisticated technology for their detection. This leads to the question of what tools we employ to capture this energy. Observatories such as LIGO, the Laser Interferometer Gravitational Wave Observatory, are designed to measure the minuscule disturbances that gravitational waves cause as they pass by. This effort is comparable to attempting to isolate a single whisper within a bustling crowd. The energy these waves carry is so subtle that its capture demands nearly infinite precision. But what if these detectors had never been built? The answer is simple. We would lose the chance to grasp a fundamental aspect of our universe. The energy of gravitational waves also prompts us to question the very fabric of the cosmos. By analyzing how these waves bend and change on their journey, we can learn about the physics governing black holes and other cosmic occurrences, making each detection another piece in the grand puzzle of the universe. It's truly compelling to realize that, as our technology improves, our capacity to interpret this energy will also grow. In time, we might become capable of detecting gravitational waves that are currently beyond our perception. This would unveil an entirely new frontier in astronomy, enabling us to investigate even more remote and ancient cosmic events. The energy from these waves also makes you reflect on the role it serves in the universe's development. Every time a cataclysmic event happens, like the merger of black holes, it doesn't just unleash energy as gravitational waves, it also alters the very structure of spacetime, leaving behind countless untold stories for us to discover. The collision of two black holes stands as one of the most awe-inspiring and mysterious phenomena in the cosmos. But what truly takes place when two of these cosmic titans meet and become one? This question invites us to delve into a celestial event that is not only captivating, but also the source of the gravitational waves we can now register here on Earth. When you think of black holes, you likely picture objects with a gravitational pull so immense that nothing, including light itself, can escape. Yet, the reality is even more complex. Black holes are not merely static voids. They are the remnants of massive stars that, after burning through all their fuel, collapsed under their own gravity. When two of these behemoths draw near each other, they enter into a shared orbit. This cosmic waltz can continue for millions of years, all while they shed energy in the form of gravitational waves. As they move closer together, their orbital dance quickens until they ultimately fuse into a single, larger black hole, releasing an incredible burst of energy. The power unleashed during this merger is so profound that in the instant of impact, it generates gravitational waves that propagate outward at the speed of light. You can imagine these waves as being similar to the ripples that spread when a stone is tossed into a pond, but their scale and implications are vastly more significant. Detecting these waves is vital because it gives us a way to observe events that would otherwise be completely hidden from our telescopes. Gravitational waves offer a new method for listening to the universe. When the LIGO Observatory first recorded a signal from a black hole merger in 2015, it was as if a new window to the cosmos had been thrown open. This signal provided detailed information about the masses of the black holes, their velocities, and the distance at which the collision occurred. Think of each black hole merger as a drumbeat echoing through the emptiness of space. Just as a drum heard from far away is quieter, the gravitational waves we receive on Earth carry faint information about events that transpired billions of light-years from us. But what is the broader impact of understanding these cosmic events? Investigating black hole mergers not only illuminates the nature of these puzzling objects, but also offers clues about how large-scale structures in the universe came to be. By piecing together how and when they combine, we can start to reconstruct the history of the universe itself. If you've ever asked yourself how galaxies were formed, the answer might be connected to these spectacular collisions between black holes, which are also linked to other fascinating processes like star formation and galactic evolution. When we discuss these black hole mergers, you should understand that we're not just talking about two objects colliding, but rather a sequence of events that resonates throughout the entire cosmos. Investigating these mergers naturally prompts the question of whether more black holes exist than we are capable of detecting. Scientists affirm that this is indeed the case, as black holes can merge even when we have no way of directly observing the event. This implies that every detection we successfully make is merely a single fragment of a much grander narrative, opening up the possibility that the universe is teeming with these mesmerizing collisions, all waiting to be discovered. Furthermore, the detection of gravitational waves provides a unique opportunity to test Albert Einstein's theory of relativity. Each time we observe one of these mergers, we can compare the data we gather against the predictions made by general relativity. This comparative process serves not only to validate the theory, but can also spark new inquiries and breakthroughs concerning the fundamental nature of space and time itself. But what is the situation with supermassive black holes? These cosmic behemoths, which reside at the cores of most galaxies, are also capable of merging. When two galaxies collide, their central black holes can eventually coalesce, unleashing gravitational waves of even greater power. This leads us to ponder the long-term consequences such monumental events will have on the future evolution of galaxies. It is truly incredible to realize that you and I are standing at the threshold of a new era of cosmic exploration. Every black hole merger we register inches us closer to comprehending not just these mysterious celestial objects, but also the deep history of the universe. As our technology continues to evolve and new observatories are constructed, the potential for groundbreaking discoveries becomes an imminent reality. These mergers are a constant reminder that the universe is filled with endless surprises, and with each new event we uncover, we become more aware of how much remains unknown. You can think of every one of these cosmic collisions as a single piece in a vast celestial puzzle. The quest for answers is ongoing, and each new gravitational wave that reaches us brings us nearer to solving the profound mysteries of the cosmos. So, I encourage you to keep your attention on the heavens, because the universe has a great deal more to share with us. Gravitational waves are akin to the echo of a remote cosmic cataclysm, a ripple in the very fabric of space-time that carries information about phenomenal events. But how is it possible for us to perceive this echo when its source is so incredibly distant? The solution is found in the coordinated efforts of different observatories, which operate like a team of cosmic detectives, working in unison to capture these faint but telling signals. Picture a symphony orchestra. Each musician contributes the sound of their instrument, and while each is beautiful alone, their collective performance is what creates a magnificent symphony. This is precisely how observatories like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo collaborate. Although each facility employs its own unique technology and methodology, together they establish a network that significantly amplifies our capacity to detect and interpret these cosmic waves. Why is this international cooperation so vital? A major challenge with gravitational waves is their extreme weakness. Much like a whisper in a crowded, noisy room, these signals can easily be lost amidst the background static of the universe. However, by combining the data from multiple observatories, signals that would otherwise be ambiguous become distinct, providing the confirmation that what was detected is a genuine cosmic event and not just random interference. LIGO, a true pioneer in this discipline, operates 2 facilities in the United States, one in Livingston, Louisiana, and another in Hanford, Washington. These 2 separate locations function like a pair of ears listening from different angles, allowing them to compare their observations to verify what they've heard. Can you imagine the significance of a wave being detected at both sites almost simultaneously? It would be analogous to 2 friends on opposite sides of the planet listening to the same song and calling each other to confirm that what they heard was real. Then we have Virgo, situated in Italy, which adds its own instrumental voice to this cosmic orchestra. Its location in Europe enables it to monitor regions of the sky that are outside of LIGO's primary field of view. Consequently, when a gravitational wave is registered by the network, the observatories can triangulate the signal's point of origin, a process similar to using 3 lighthouses to pinpoint the exact location of a vessel lost in the dark. And the collaboration extends even further. Imagine you are at a gathering where every guest contributes something unique. One provides the food, another the music, and a third brings a movie. Their combined offerings result in an unforgettable shared experience. In the field of gravitational wave astronomy, cosmic events can also be accompanied by other signals, like gamma rays or even visible light. Merging information from all these different observational sources allows us to construct a much more complete and detailed picture of the event. What are some of the difficulties these observatories must overcome? Distance presents a formidable obstacle. For instance, a gravitational wave might pass through our planet but fail to be registered at one specific location. By having multiple observatories strategically positioned across the globe, we can effectively capture and validate a signal before it dissipates. This global network is absolutely essential for confirming detections and ensuring that we are not being misled by instrumental noise. Have you ever considered what it must be like for these teams to work together across continents? It's very much like assembling a complex puzzle, where each person holds a critical piece that completes the whole image. The first gravitational wave signal detected by LIGO in 2015 was a landmark moment in science. But that single achievement was the culmination of many years of dedicated collaboration and collective effort from the global scientific community, which united to decipher the signal and pinpoint its source. Moreover, the technologies these observatories rely on are nothing short of revolutionary. They are like telescopes that don't just see the sky, but actually listen to the vibrations of spacetime. Their detectors are sensitive enough to measure changes in distance smaller than the diameter of a single proton. To put that into perspective, It's like trying to measure the difference in the length of two guitar strings while standing in the middle of a loud rock concert. It's truly astonishing when you think about it. Gravitational waves are not only captivating subjects of study in their own right, they also provide us with entirely new methods for exploring the universe. With every signal an observatory detects, another window is opened onto a previously unseen corner of the cosmos, promising more discoveries for you to witness in the future. Whenever you encounter the subject of gravitational waves, I encourage you to envision them as a grand cosmic symphony. In this composition, every signal we register is a vital note, moving us nearer to comprehending our own place within the universe. These waves serve as the echoes from the cosmos's most powerful events, a celestial melody that chronicles the tales of cosmic collisions and mergers. Their most remarkable quality is the ability to exist at various frequencies, each of which unlocks a distinct secret about the fabric of spacetime. Much like different musical notes combine to create unique harmonies, the various forms of gravitational waves allow us to decipher events happening in the most remote corners of the cosmos. The specific frequency of these ripples is determined by the nature of the cosmic event that produced them. For instance, when a star detonates in a supernova, it radiates high-frequency gravitational waves, which you can think of as the sharp, piercing notes from a piano. These vibrations travel across space, carrying the indelible signature of that colossal explosion. Conversely, what occurs when two black holes coalesce? Such an event generates low-frequency gravitational waves, comparable to a deep, resonant bass line in the cosmic orchestra. Each kind of wave conveys its own distinct story. High-frequency signals give us the ability to study phenomena that happen over very brief periods, such as the merging of neutron stars. This type of event is so incredibly energetic that, like a flash of lightning, it creates waves that can be measured with extraordinary precision. Low-frequency waves, however, often point to far more gradual processes, like black holes circling each other for millions of years before their final, inevitable collision. To understand this better, imagine yourself attending a concert where an orchestra plays a variety of pieces, each with its own tempo and tune. The gravitational waves in our universe behave similarly, with every frequency providing a unique viewpoint on cosmic happenings. The key question, then, is how we can determine which frequency matches a particular event. This is where the scientific process is essential, as researchers have crafted theoretical models that forecast the expected signals from different kinds of cosmic phenomena, effectively giving us a musical map to navigate the symphony of the universe. The discovery of gravitational waves has truly opened a new frontier in the field of astronomy. Before this, our observations were limited to light, which is like viewing the universe as a painting in a gallery. Now, with our ability to detect these waves, we can actually listen to the cosmos, as if we were present at a celestial concert. This new auditory perspective grants us insight into events that were previously completely invisible to us. Among the most significant accomplishments in this area was the successful detection of a black hole merger. The frequency of the resulting waves provided direct information about the masses of the black holes involved, a priceless detail that deepens our understanding of the universe of these mysterious cosmic giants. Furthermore, analyzing different frequencies can aid our study of galactic evolution. By tuning into low-frequency waves, we might capture the echoes of events from billions of years ago, offering a singular look into the universe's ancient past, like receiving a message from a long-lost acquaintance describing their world. Collaborative efforts between observatories like LIGO and Virgo are crucial, as they enable us to merge data from various frequencies to construct a more thorough depiction of cosmic events. You can picture this as different musicians in an orchestra uniting to perform a complex symphony, with each one contributing their unique part to create something far greater. By working in concert, they can uncover patterns that would likely be missed if we were observing through only a single frequency. But what if the event under study is so intricate that it radiates waves across a wide spectrum of frequencies? In these cases, the science becomes a captivating puzzle. Astrophysicists must labor to decode the information by analyzing all the different waves, much like someone assembling a cosmic jigsaw puzzle, meticulously fitting each piece to reveal the complete image of the event. Gravitational waves also grant us the ability to perceive phenomena that are impossible to see with conventional telescopes. Imagine you are trying to know what is behind a solid wall. With only a flashlight, you would be unable to see past it. However, if you could listen for sounds, you might be able to sense what lies on the other side. In this way, gravitational waves are our method of listening to the universe, unveiling events that would otherwise stay concealed from our sight. The capacity to detect different frequencies of gravitational waves not only enriches our comprehension of the cosmos, but also introduces a host of new questions. What other celestial events could be occurring at this very moment, sending out waves we have yet to identify? Each new discovery propels us toward new mysteries, inspiring us to press onward in our exploration and never become complacent in our quest for answers. It feels as though every new detection is another chapter in a book that never fails to astonish us. The partnership between LIGO, Virgo, and other observatories extends far beyond mere detection. It is a constant flow of ideas and breakthroughs. The sheer volume of shared information, from data analysis techniques to theories on the meaning of these signals, fuels an enriching dialogue that drives science forward. This collective effort brings us ever closer to unraveling the deepest mysteries of the universe. And, with new observatories being built and technologies advancing, the potential for future discoveries is simply staggering. This grand adventure is truly just getting started. Ultimately, the narrative conveyed by gravitational waves reminds us of the sheer scale and intricacy of the cosmos. These discoveries demonstrate that while you might feel minuscule in the face of the universe's immensity, every new insight brings us closer to grasping our own place within it. Today, we're exploring one of modern science's most captivating frontiers, multi-messenger astronomy, a journey of understanding that is only just beginning. Have you ever considered how scientists achieve a more holistic view of the universe? The key is to synthesize the various types of signals that travel to us from deep space. Much like a detective gathers multiple forms of evidence to unravel a case, astronomers rely on a diverse set of cosmic messengers to decode the universe's secrets. This approach has revolutionized astronomy in ways we could never have foreseen. Picture a grand concert where the music isn't produced by a single instrument, but by an entire symphony orchestra. Every instrument adds its unique sound, and their combination results in a rich, layered musical tapestry. In the cosmos, these instruments are the different forms of radiation we can perceive, such as gravitational waves, visible light, and X-rays. Each one provides a distinct viewpoint on the celestial events unfolding across the vastness of space. Gravitational waves, which are essentially ripples in the very fabric of space-time, represent just one element of this cosmic symphony. When we detect them, they offer priceless information about cataclysmic events like the merging of black holes. However, when we combine this data with other forms of radiation, we unlock a far more comprehensive and detailed picture of the event. Think about assembling a jigsaw puzzle. While every individual piece holds some value, the complete image only emerges when you connect them all. By integrating gravitational waves with electromagnetic radiation, astronomers can tackle questions that were once impossible to answer. For instance, understanding the moments just before two black holes collide requires clues from gravitational waves. But the light from the explosion is equally vital for a full explanation. Now, imagine receiving only a fragment of a message from a friend, leaving you with numerous unanswered questions about the full story and the reactions of others involved. This is precisely the situation astronomers face with incomplete data. By merging information from both gravitational waves and light, they can resolve these uncertainties and achieve a much deeper comprehension of cosmic phenomena. The detection of the event designated GW170817 marked a true watershed moment in the history of astronomy. This single occurrence delivered not only gravitational waves, but was also witnessed across the entire electromagnetic spectrum, from gamma rays to visible light. This allowed us to compile data that painted a remarkably complete portrait of what transpired, akin to receiving simultaneous accounts from several witnesses to the same event. But what does this new capability truly signify for our cosmic understanding? Multi-messenger astronomy paves the way for novel theories and revolutionary discoveries, enabling us to observe phenomena that were entirely invisible to us before. For example, the study of stellar explosions, known as supernovae, has been greatly enhanced by this integrated approach, allowing us to see not just the light from the star but also its effect on the surrounding space. Our innate human curiosity drives us to explore what lies beyond the limits of our vision, and multi-messenger astronomy is a perfect tool for this quest. If you were in a dark forest, able only to hear its sounds, switching on a flashlight would reveal not just the trees, but also the hidden creatures among them. Combining different data types works in the same way, illuminating our scientific path with newfound understanding. Gravitational waves are a permanent new fixture in our toolkit. But what does the future have in store? As technology advances, and we build more sophisticated telescopes and observatories, the power of multi-messenger astronomy will only grow. Imagine a future where you can receive simultaneous messages from multiple cosmic sources, weaving an even richer and more intricate narrative of the universe. Scientists are working relentlessly to enhance our capabilities for detection and analysis, as each new signal presents an opportunity to learn more about the cosmos. Collaboration among different observatories is essential to this effort. Just as a research team unites to solve a complex puzzle, facilities around the globe are coordinating to better comprehend the universe's mysteries. The search for life on other planets also reaps significant benefits from multi-messenger astronomy. By combining data from various instruments, astronomers can analyze the chemistry of alien atmospheres for potential signs of life, an endeavor that often demands the integration of diverse scientific disciplines and technologies. The thrill of this research extends beyond the scientific community, inviting all of us to participate in this grand adventure. Ultimately, multi-messenger astronomy shows us that the universe is a profoundly interconnected system, where every signal tells a piece of a larger story, and every breakthrough brings us closer to understanding our role in it. The exploration of the cosmos is a journey without end. Each answer we find sparks new questions, and every discovery unlocks new frontiers. So the next time you gaze at the night sky, remember that there is far more than what you can see. A celestial symphony is playing, and we are just now learning how to listen. To fully appreciate this, you need to return to 2017, when a signal detected by scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, set astronomical research on a new trajectory. Picture a pair of black holes. those enigmatic and dense celestial objects, locked in orbit around one another. As they spiral inward, their rotation accelerates, resembling two dancers in a quickening waltz that concludes with a phenomenal cosmic merger. A collision that generates gravitational waves. What made the event known as GW170817 so extraordinary was that the merger of these objects produced not only detectable gravitational waves, but also a flash of light, referred to as a kilonova. It was as if the universe was communicating with us in two distinct languages simultaneously, one through the vibrations of spacetime and the other through visible light. This capacity to both hear and see the same cosmic event is a landmark achievement for science. Think of it as being at a concert, where you can physically feel the music's vibrations through the floor, while also hearing the melody with your ears. This synergy, created by combining gravitational wave data with light from the kilonova, yields a far more complete picture of cosmic events. This discovery was pivotal because it not only validated theories on how gravitational waves are produced, but also ushered in a new era of cosmic observation, multi-messenger astronomy. Now, every cosmic event presents an opportunity not just to listen for gravitational waves, but also to see through various forms of electromagnetic radiation, including visible light and gamma rays. The GW170817 event itself supplied a trove of invaluable data, offering insights into the nature of black holes and their mergers. For instance, it revealed that the black holes involved were more massive than previously theorized, raising compelling questions about what other secrets the cosmos may hold. Gravitational waves give us a novel method for perceiving the most cataclysmic events in the universe, meaning older astronomical techniques based solely on light must now be augmented by these cosmic vibrations. The detection of GW170817 was more than a technical victory. It galvanized the global scientific community, uniting researchers from various fields in a collective endeavor to decode the universe, much like a team of detectives solving a long unanswered case by pooling their clues. As you reflect on the legacy of GW170817, you can anticipate an exhilarating future for astronomy, with new observatories being constructed and detection methods constantly being improved. Think of gravitational waves as ripples spreading across a pond. When a stone is tossed into water, waves radiate outward. Similarly, in space, these ripples are created by profound cosmic events like the merging of black holes or neutron stars. Each time such an event occurs, space-time itself trembles, and we can now detect those vibrations here on Earth. The detection of these waves is just the start. In the years to come, we might be able to observe phenomena we have yet to even imagine, from witnessing the birth of a black hole to capturing a signal from an event that happened billions of years ago. Each new finding moves us closer to resolving fundamental questions about the universe's origin, nature, and ultimate destiny. Technological progress is the engine driving this new epoch of discovery. Scientists are continually developing more sensitive and sophisticated instruments. Imagine a telescope capable of not just seeing celestial light, but also hearing the harmonies of the cosmos. With every new instrument, our ability to detect gravitational waves grows more precise, expanding the potential for uncovering the universe's deepest mysteries. The future of gravitational wave astronomy also lies in exciting international collaborations between observatories. As more facilities like LIGO and Virgo coordinate their efforts, the detection network becomes a global symphony, By working in unison, they may one day capture a cosmic event so profound that it completely transforms our very understanding of physics. Scientific collaboration on an international scale not only speeds up the process of discovery, but also vastly enriches our collective understanding. The study of the cosmos extends far beyond just gravitational waves, raising the question of how this new way of observing the universe connects with fields like astrophysics and cosmology. By merging gravitational wave data with observations from light, X-rays, and other electromagnetic radiation, we are beginning to paint a much more detailed and comprehensive portrait of the universe. In this way, the field of multi-messenger astronomy is poised to completely reshape our knowledge of cosmic events. One of the most thrilling prospects is the potential for future technologies to allow us to witness events that are currently beyond our reach. Imagine, for example, the ability to detect the collision of black holes taking place at the very edge of the observable universe. Such a feat would not only represent a monumental scientific achievement, but could also offer profound insights into the nature of dark matter and dark energy, which remain two of the biggest puzzles in modern cosmology. Gravitational waves also hold the potential to illuminate the mechanics of the universe's expansion. As scientists delve deeper into this research, we may uncover how these cosmic ripples are linked to the accelerating expansion of space itself. This knowledge could fundamentally alter our theories about why and how the universe is in a state of constant evolution. Additionally, observing phenomena like supernova explosions through gravitational waves can provide us with vital clues about the birth and life cycles of stars, with each new detection acting as a crucial piece of a cosmic puzzle. It is truly remarkable to consider the eventual impact these breakthroughs will have on society, and how our perception of our own place in the cosmos will be transformed. Science has always been a powerful engine for change, and as our comprehension of gravitational waves deepens, so too does our understanding of our own existence. Education is a vital component of this journey. As discoveries are made, it is essential to communicate them to the public in a way that is both clear and engaging. Human curiosity is boundless, and nurturing an interest in science can inspire the next wave of innovators and thinkers. The years ahead are filled with promise, and the scientific community is buzzing with anticipation for what new revelations await. Every fresh advancement in gravitational wave detection has the power to trigger a paradigm shift in our thinking. The exploration of the universe has never been a more exhilarating endeavor, and as we continue on this path, it is crucial that you maintain both an open mind and an unyielding sense of curiosity. Ultimately, the future of this field is not merely about finding answers to old questions, but about formulating entirely new ones, charting a course toward knowledge we haven't yet imagined. For decades, the Great Attractor has remained an enigma that has captivated astronomers and scientists alike. To truly grasp what this phenomenon is and why it holds such importance for our understanding of the universe, you must first immerse yourself in the intricate dance of galaxies and the powerful gravitational influence it commands. Picture the cosmos as a boundless ocean filled with galaxies, each navigating its own unique course. Somewhere within this expanse lies an unseen point that functions as a gravitational lighthouse, pulling everything towards it. This gravitational focal point is what we call the Great Attractor, situated in the direction of the Centaurus constellation. Although it is impossible for you to see it directly, its immense presence is clearly revealed by the motion of the galaxies that surround it. The key to its influence lies in gravity. Much like a magnet pulls on metal, the Great Attractor exerts a formidable force that warps the paths of nearby galaxies. As our own galaxy and its neighbors are drawn toward this point, scientists theorize it must be an incredibly dense region of space, perhaps a massive concentration of both galaxies and dark matter. Attempting to observe the Great Attractor directly is like trying to spot a distant landmark through a thick, obscuring fog. Our galaxy, the Milky Way, is positioned right in the middle of this stellar haze, which makes a clear view of the region nearly impossible. To overcome this, astronomers employ ingenious techniques, such as meticulously studying the movements of galaxies that are streaming toward the Great Attractor, to deduce its existence and map its characteristics without ever laying eyes on it. One of the most compelling questions is how the Great Attractor is steering the motion of our very own galaxy. The Milky Way is being pulled toward this unseen destination at a truly astonishing speed, creating a sensation of acceleration not unlike the feeling you get on a roller coaster plunging down a steep hill. This raises profound questions about our cosmic future, suggesting we may be on an endless voyage toward a destination we may never fully comprehend. The relationship between the Great Attractor and the expansion of the universe presents another fascinating area of study. While the cosmos is steadily expanding, pushing galaxies further apart, the Great Attractor serves as a powerful local anchor. It continues to exert its immense gravitational pull, challenging the universe's overall tendency to spread out. This creates a kind of cosmic tug-of-war, with the forces of universal expansion pitted against the immense localized attraction of this mysterious object. The quest to understand the Great Attractor has gained significant momentum in recent years, driven by the development of new technologies and observational methods. This effort is akin to using a far more powerful telescope to finally peer through the fog at something that was once completely hidden. The ongoing investigation could reveal that the Great Attractor is, in fact, a colossal cluster of galaxies in the process of colliding, a discovery that would reshape our map of the local universe. Could the Great Attractor be a clue to an even more vast cosmic architecture that we have yet to comprehend? It's captivating to consider how it relates to other immense structures, such as the Virgo supercluster, which also directs the flow of galaxies. Much like a group of individuals at a party who subtly affect one another's movements, these cosmic behemoths might be engaged in a gravitational waltz that shapes the destiny of our entire galactic region. Investigating the Great Attractor does more than merely clarify the mechanics of galactic motion. It compels you to ask deeper questions about the very nature of the universe. It makes you wonder if we are truly alone in this immense space, or if other similar points of attraction await discovery. Every answer we uncover about this phenomenon simply unlocks more questions, beckoning us to delve deeper into the cosmic unknown. The search for life on other worlds is surprisingly intertwined with our study of the Great Attractor. If this gravitational anomaly steers the course of entire galaxies, you have to ask how that influence might affect the formation of planetary systems, and, by extension, the potential for life. It serves as a powerful reminder that every element in the cosmos is linked in ways that often defy our imagination. As we probe this cosmic enigma, it is vital to recognize that the hurdles in astronomy demand more than simple observation. Unlocking the secrets of the Great Attractor requires both advanced technology and seamless collaboration among scientists around the world. In fact, millions of brilliant minds are currently uniting their efforts, all driven by a shared desire to piece together our cosmic history. Our exploration of the Great Attractor is only in its initial phase, set to accelerate as our technology evolves and our instruments become increasingly sophisticated. The future of this research is incredibly exciting, filled with promise. What amazing discoveries are waiting for us just over the horizon? It's possible that we are closer than we think to solving the great mysteries of gravity and the universe's fundamental structure. In the end, the Great Attractor remains a profoundly fascinating cosmic feature that encourages you to reflect on galactic dynamics and the overall architecture of the cosmos. As our quest for knowledge presses forward, each new question brings us a step closer to understanding our place in this vast reality. The journey is just getting started, and this gravitational anomaly may be the very key to unlocking much deeper, universal truths. The zone of avoidance is a captivating term in astronomy, and its name alone conjures a sense of profound mystery. Have you ever felt disoriented in a maze, searching for a way out only to find that some sections are completely hidden from view? This is the experience astronomers have when they attempt to study the region of the Great Attractor. This pivotal cosmic feature is concealed behind the dense plane of our own Milky Way galaxy. To truly appreciate what this means, you first need to understand that the Milky Way is far more than just a band of stars in the night sky. It is a sprawling disk of stars, gas, and dust that forms a veritable cosmic labyrinth. When we aim our telescopes toward the galactic center, thick clouds of interstellar material obstruct our line of sight, much like trying to see through a dirty window. The view beyond may be spectacular, but the grime makes it impossible to see clearly. So, why is the Great Attractor considered so important? This isn't just another location in space. It is an enormous concentration of mass that powerfully influences the trajectories of all surrounding galaxies. Imagine you are on a densely packed dance floor where everyone is moving randomly. Suddenly, a large group begins to move in a single direction, and its momentum pulls everyone nearby along with it. This is essentially the gravitational pull the Great Attractor exerts on its cosmic neighbors. The fundamental challenge is that we cannot observe it directly. While astronomy has made incredible leaps, the zone of avoidance persists as an unsolved puzzle. The sheer quantity of gas and dust places conventional optical telescopes at a significant disadvantage, akin to attempting to read a book with pages that are glued shut. However, scientists have found ways to indirectly perceive what's happening behind this cosmic veil by using other wavelengths, such as infrared and radio waves, essentially using different senses to hear what cannot be seen. This raises the ultimate question: what actually lies beyond this obscured region? Using a variety of tools, astronomers have managed to infer the existence of massive structures by observing their gravitational pull on their surroundings. But this isn't enough. There is still so much more to learn. What do you think will happen when we can finally peer behind the zone of avoidance? The information we gather could rewrite our understanding of the universe's structure and the forces that govern galactic movement. Scientists are also trying to determine how the Great Attractor relates to the ongoing expansion of the universe. As space itself expands, this gravitational anchor point isn't static. Its influence likely evolves over cosmic time. You can think of it like a party where guests are constantly arriving and leaving, which alters the social dynamics within the room. Understanding how this changing influence affects the interactions between galaxies is a major focus of modern cosmology. For astronomers, every new clue is a significant opportunity. Exploring the zone of avoidance is not just about identifying what's inside it, but also about understanding how everything in the cosmos is intricately connected. Galaxies, much like us, are not isolated. They exist in a state of constant interaction, governed by forces we are only now beginning to comprehend. As we continue on this quest, you can be sure that technology will play the most crucial role in lighting the way forward. Out in the vastness of the universe, certain structures exist that defy our current comprehension and compel us to gaze beyond our known horizons. The South Pole Wall is one such cosmic marvel, a phenomenon resting at the very edge of our celestial understanding. To grasp what it is, try to picture space as a boundless ocean with entire galaxies akin to floating islands. In this cosmic sea, the South Pole Wall emerges as a colossal landmass, a frontier defined by an immense concentration of galactic matter. This incredible gathering of galaxies captivates us not just for its sheer scale, but also for the fundamental questions it poses about the very architecture of the universe, such as how it formed and what its existence implies for cosmic expansion. A remarkable detail is that the South Pole Wall is almost entirely hidden from our view. It is positioned behind the dense plane of our own Milky Way, making direct observation incredibly difficult, much like trying to admire a stunning landscape through a grimy windowpane. Despite this, astronomers have confirmed its presence by carefully tracking the movements of galaxies in its vicinity. The South Pole Wall is actually a component of an even grander formation called the Virgo supercluster. You can imagine this supercluster as a vast, interconnected network of cosmic highways, with the South Pole Wall functioning as one of the great bridges that links different regions of this system. This entire network is staggering not only in its dimensions, but also for the crucial influence it exerts on the clustering and motion of galaxies throughout the cosmos. So, what is this structure's effect on the expansion of the universe? Gravity is the fundamental force that weaves everything together, and as the cosmos stretches outward, the South Pole Wall generates a powerful gravitational pull that influences neighboring galaxies, drawing them inward. It behaves like an enormous magnet, altering the trajectories of countless star systems around it. It makes you wonder what the universe might look like if these massive structures had never formed. The very existence of the South Pole Wall also leads to profound questions about the essence of space and time. It's possible that as the universe expands, these enormous structures are interconnected in ways that we have yet to grasp. Perhaps sometime in the foreseeable future, we may find that the South Pole Wall is not merely a boundary, but a gateway to entirely new dimensions of reality. Of course, scientific progress is rarely without its challenges. The position of the South Pole Wall behind the Milky Way presents a formidable obstacle for researchers. To study this region, astronomers must employ innovative techniques, using telescopes that can detect a wide spectrum of light, from radio waves to X-rays, to capture the essence of what is concealed behind our own galaxy. Fortunately, technology is advancing at an incredible pace, and new instruments are constantly being developed to help us transcend our current limitations. But just imagine what will happen when we can finally see the South Pole Wall directly. What astonishing revelations might be waiting for us? This mystery injects an additional layer of thrill into our exploration of the cosmos. Investigating this structure also pushes us to contemplate our place in the universe. For if the wall is a marker for dark matter and dark energy, it could completely reshape our understanding of physics. Dark matter, though invisible, is known to be a key ingredient in the formation of galaxies and other large-scale structures. We must always keep in mind that exploring the cosmos is a perpetual journey, where each new finding only uncovers more questions and opens new avenues of research. The South Pole Wall represents just one component of this immense cosmic puzzle, yet studying it could offer vital insights into the ultimate destiny of the universe. This work also showcases the power of scientific collaboration, as astronomers worldwide share data and resources to unlock these secrets, functioning like a great orchestra in which every instrument contributes to a symphony of knowledge. Ultimately, the South Pole Wall serves as a reminder that, while the universe is profoundly vast and mysterious, every discovery brings us a little closer to the truth. One day, we may be able to peer through the veil of the Milky Way and witness the grandeur of this cosmic wall in all its splendor. The expansion of the universe itself is a captivating phenomenon, one that encourages us to examine the behavior of gravity within a cosmos in constant flux. Have you ever considered how this expansion connects to another great mystery, the Great Attractor? To figure that out, we first need to delve into what this enigmatic object is and how it shapes the movement of galaxies. Future telescopes and observatories will be far better suited to pierce these veils of gas and dust, giving scientists the ability to witness phenomena that have remained invisible until now. Each technological leap forward provides us with a new set of lenses, empowering us to see deeper into space than ever before. Our fascination with cosmic enigmas like the zone of avoidance and the Great Attractor also reminds us of the humility we must maintain in the face of such a vast universe, where every answer we uncover inevitably leads to new questions. In this unending quest, each discovery, regardless of its size, inches us closer to understanding our own place in the cosmos. As we continue our exploration and attempt to solve the riddles of these great structures, it's important to remember that science is a journey filled with surprises. In this grand endeavor, our curiosity is the most reliable guide, and the pursuit of knowledge is the very light that illuminates our path forward. In a particular region of space, there is an immense gravitational force known as the Great Attractor, which powerfully pulls on the galaxies surrounding it. If you picture the universe as a vast ocean with galaxies adrift on its surface, the Great Attractor acts like a colossal current, drawing everything toward its core. This naturally leads to a question. What is located at the center of this cosmic river? And what gives it such extraordinary power? Scientists have determined that the Great Attractor is an incredibly dense concentration of matter, composed of entire galaxies and galaxy clusters. Its gravitational pull is so profound that it can steer the motion of billions of stars across the cosmos. This raises a fascinating dilemma concerning the expansion of the universe. The key to understanding this dynamic is recognizing that while the universe expands, the Great Attractor's gravity functions as a powerful brake, pulling galaxies back toward itself. Imagine you're on a cosmic dance floor, where some dancers are constantly moving away from each other, while others are being steadily drawn toward the center. The expansion of the universe, a discovery from the 20th century, has been a central topic for astronomers ever since. Space itself is stretching, causing galaxies to drift apart, yet the gravitational influence of the Great Attractor can partially resist this universal trend. Think of it like a balloon that is being inflated. As the surface expands, some points drawn on it might still feel a pull toward a central location. As the cosmos stretches, the way galaxies group together also evolves. Some are gathered around the Great Attractor, while others may continue to move away. This interaction prompts a compelling question about how gravity shapes the distribution of galaxies across the immense expanse of space. The future of our universe is another profound subject the Great Attractor forces us to consider. If the cosmos continues its expansion, what will become of the galaxies caught in the Great Attractor's grasp? Some theories propose that these galaxies may eventually be drawn together, their trajectories altered to forge a new cosmic order, and perhaps even form a single massive supergalaxy in the far distant future. It is truly astonishing to contemplate that forces of such a massive scale exist, capable of shaping the very structure of our boundless universe, with the Great Attractor's gravity being a prime example. This cosmic tug-of-war, pitting the outward push of expansion against the inward pull of attraction, reveals the universe as a complex and dynamic arena, where every component has a significant role to play. As our explorations continue, more questions surface. such as how dark matter influences this interaction. Comprising the majority of the universe's mass, dark matter could be a critical element in determining how the great attractor's gravity affects surrounding galaxies. The quest for answers reveals that for every new discovery we make, we uncover even more profound mysteries waiting to be solved. Ultimately, the story of the Great Attractor is a remarkable chapter in the annals of astronomy, teaching us that the universe is in a perpetual state of flux. So, the next time you gaze up at the night sky, I hope you'll remember the invisible forces at play, shaping the destinies of countless galaxies. Your curiosity and desire for exploration are what will continue to unlock the secrets of the cosmos. Turning our attention closer to home, Ganymede, Jupiter's largest moon, presents a fascinating case that has captured the imagination of scientists and space enthusiasts. You might wonder what makes this particular moon so significant in our search for extraterrestrial life within the solar system. The answer, as you'll see, is more compelling than you might first suspect. To begin with, Ganymede is far from being an ordinary moon. With a diameter of over 5,200 kilometers, it is larger than the planet Mercury. More importantly, it harbors something Mercury does not: a vast ocean of liquid water hidden beneath its icy crust. This is not a minor body of water, but an immense ocean that may hold more water than all of Earth's oceans combined. The presence of liquid water is considered a fundamental prerequisite for life as we know it, because here on Earth, life is found wherever water exists. This raises the tantalizing possibility: could Ganymede's hidden ocean support some form of life? While we aren't envisioning complex creatures from science fiction, discovering even microscopic organisms would represent a truly revolutionary breakthrough for humanity. Furthermore, Ganymede possesses its own magnetic field, a feature that is exceptionally rare among moons in our solar system. This magnetic field could shield a potential atmosphere from harmful cosmic radiation, thereby fostering a more stable and hospitable environment. Determining whether such an atmosphere exists is a crucial next step, as its presence would dramatically increase the chances that life could have emerged and survived there, making the exploration of Ganymede a major scientific imperative. Furthermore, Ganymede possesses its own magnetic field, a feature that is exceptionally rare among moons in our solar system. This magnetic field could shield a potential atmosphere from harmful cosmic radiation, thereby fostering a more stable and hospitable environment. Determining whether such an atmosphere exists is a crucial next step, as its presence would dramatically increase the chances that life could have emerged and survived there, making the exploration of Ganymede a major scientific imperative. In the coming decade, NASA's Europa Clipper mission is slated for liftoff, promising to seek answers not just about Europa, Jupiter's most renowned moon because of its ocean, but about Ganymede as well. This suggests we could soon have new information regarding what is hidden beneath its massive sheet of ice. Just consider for a moment if Ganymede were proven to be habitable. What consequences would this discovery have for our entire conception of the cosmos? It would fundamentally alter our perspective. The chance that we are not isolated in the universe would suddenly feel much more real. The notion that life can emerge in varied locations and under diverse circumstances could unlock a spectrum of possibilities that we have never before contemplated. But what form would this life take? It might not be complex organisms, but rather bacteria or other single-celled life forms, yet its discovery would still be a find of immense significance. Science is progressing with incredible speed, and every new mission draws us nearer to the solutions that have captivated humanity for ages. Ganymede, with its concealed ocean, may hold one of the crucial keys to solving these cosmic riddles. Moreover, it's fascinating to think about how the exploration of Ganymede could reshape our view of our own place in the universe. If we discover life in such a distant part of our solar system, what would that reveal about Earth and our ongoing quest for life on other worlds. Scientists are thrilled by the prospect that Ganymede could serve as more than just a subject of astronomical study, but as a genuine natural laboratory. By studying samples from its surface and any potential atmosphere, we could unlock secrets about how celestial bodies are formed and how life evolves under the most extreme conditions. The existence of life on Ganymede, while it may seem like an otherworldly idea, remains a tangible possibility. As science continues to advance, each new finding prompts a fresh set of questions. What else might be waiting in our solar system that we have yet to investigate? What other worlds could harbor conditions suitable for life? Ultimately, Ganymede is far more than just one of Jupiter's moons. It stands as a testament to a universe brimming with surprises. The search for life in its hidden ocean is an expedition that is only just getting started. And as our exploration continues, we might learn that life, in its many forms, is more prevalent than we ever dared to believe. The concept of the speed of light has captivated scientists and curious minds for centuries. Are you aware that in a vacuum, light travels at a velocity of roughly 300,000 kilometers per second? To put that into perspective, it's equivalent to circling our planet 7 times in a single second. But what does attaining such a speed truly signify? Even more compelling is the question of whether anything can move faster than light. When you think about light, its velocity is often the first thing that comes to mind, but its fundamental nature holds a profound mystery. Light behaves both as a wave and as a particle, seemingly leading a dual existence that defies our everyday intuition. What would it feel like to travel at the speed of light? According to Einstein's theory of relativity, time itself begins to act in very peculiar ways as you approach this velocity. For an individual traveling at light speed, time would actually slow down, meaning a journey of mere minutes for the traveler could correspond to many years for those left behind on Earth. One of the most significant mysteries is that, based on the theory of relativity, it's impossible for anything to surpass the speed of light. But what about phenomena that appear to challenge this fundamental rule? Fascinating concepts have been put forward, such as tachyons, hypothetical particles theorized to move faster than light. To this day, however, we have found no evidence that they actually exist. Are they real and simply awaiting discovery, or are they just a physicist's theoretical daydream? Let's also consider wormholes. Can you picture taking a shortcut directly through the fabric of spacetime? The concept may sound like something from science fiction, yet wormholes emerge as mathematical solutions within the equations of general relativity. If they could exist, they would be able to link 2 remote points in the universe, enabling instantaneous travel between them. The current reality, however, is that we have never detected one, and we remain unsure if they could ever be created or stabilized. The twin paradox offers another captivating illustration of these principles. Picture a pair of twins. One embarks on a journey aboard a spaceship moving at nearly the speed of light, while the other remains on Earth. When the traveling twin returns, they will have aged significantly less than their sibling. This effect, which seems torn from the pages of a novel, is a direct outcome of relativity. But how can this be reconciled with our daily experience of time passing uniformly for everyone? The speed of light also dictates how we fundamentally perceive the universe. When you gaze at the stars, you are actually observing light that has journeyed for years, or even centuries, just to reach your eyes. For instance, if a distant star were to explode in a supernova, you wouldn't witness the event until many years after it happened. This forces you to reflect on the immense scales of time and distance in the cosmos, and on how our observations are merely echoes from the distant past. Throughout history, scientists have explored ways to overcome this ultimate speed limit. From theories of warp drives to concepts involving the use of antimatter, the ambition to break the light-speed barrier has fueled some of the most brilliant minds. But challenging the very laws of the universe comes with a cost. Some theories propose that crossing this boundary would demand an unimaginable quantity of energy, far more than we can currently generate. And as we strive for new horizons, we also run into profound ethical questions. Imagine if you could one day surpass the speed of light. Would you then bear responsibility for everything you might find? Could you rewrite history or change the destiny of entire worlds? Science fiction often confronts us with such ethical questions, which, though hypothetical, force you to reflect on the repercussions of our technological leaps. In the world of quantum physics, the principle of non-locality proposes that particles can be interconnected in ways that defy our conventional understanding of space and time. This very idea makes you question the fundamental rigidity of the universe, suggesting that, at its core, reality might be far more flexible than we perceive. Concepts surrounding faster-than-light travel also compel you to reconsider what you know about time itself. Some scientists theorize that time is not a straight line, but a more fluid dimension, a notion that could unlock entirely new perspectives on our existence. The question is, are you prepared to entertain the possibility that your perception of time is simply a human-made framework? This entire journey through the physics of light speed has led us through both scientific and philosophical territories. The drive to comprehend this universal limit raises profound questions, not only about the cosmos, but also about your own place within it. Ultimately, the speed of light is more than a physical constant. It is a standing invitation to continue questioning and exploring the unknown. In the end, while the velocity of light establishes a boundary in our universe, human inquisitiveness is limitless. Science is in a constant state of evolution, pushing back against our established beliefs and widening our horizons. The questions that emerge from this journey are just as vital as the solutions you seek, placing us at a thrilling point in history, where every new insight could be a step toward solving cosmic mysteries. So, what does the future hold? Perhaps only time and light itself can reveal the answer. Humanity's exploration of the cosmos has always been an infinite adventure, one that forces you to ponder your role in the grand scheme of things. Gravitational waves, which are faint tremors in the very structure of spacetime, represent one of the primary tools for unlocking the universe's secrets. But what makes them so profoundly significant? It's like gaining the ability to listen to cosmic events, not with telescopes that see light, but through vibrations that recount tales of cosmic collisions and spectacular phenomena. This capability naturally leads to the question of what these waves are actually communicating. Each time a massive star collapses or two black holes collide, they send out gravitational waves that travel across the cosmos. By capturing these ripples, you can access information about events that were once completely hidden from view. It is as though the universe has started speaking in a language that we are only now beginning to decipher. Now, you should consider the significance of research in this area. The detection of gravitational waves does more than just let us witness extreme cosmic events. It fundamentally changes our grasp of physics. It compels you to re-evaluate what you thought was settled knowledge about gravity and the makeup of the universe. What if you could merge this new observational method with other scientific fields? Multi-messenger astronomy provides just that. Combining gravitational wave data with information from electromagnetic radiation to create a much clearer, more complete picture. Human curiosity is truly insatiable, driving you to ask how a phenomenon as abstract as gravitational waves could have any real impact on your everyday life. By achieving a deeper understanding of the universe and its underlying principles, you can translate that knowledge into technologies that enhance life on Earth. From next-generation communications to revolutionary medical advances, fundamental science consistently shapes our world in practical ways. As you look toward the future, it is only natural to wonder what other discoveries are waiting to be made. The study of gravitational waves is still in its infancy, and every new signal we detect raises deeper, more intricate questions. What are the true boundaries of the universe? Could there be other dimensions that you have yet to perceive? Science often feels like an immense library, where each book you open reveals entirely new volumes about our existence. These gravitational waves, much like the ripples spreading across a pond, might appear subtle, yet their implications are vast. How can something so remote and seemingly insubstantial alter your perception of reality? The answer is that in studying the universe, you are not just searching for answers to external questions. You are also on a journey of self-discovery. Each new finding draws you closer to comprehending your own existence and the true nature of the reality you inhabit. Throughout this exploratory journey, you must also acknowledge the critical role of collaboration. Scientific progress is a collective endeavor, with networks of observatories like LIGO and Virgo working in concert to decode the cosmos's secrets. It is truly remarkable to think that through such partnerships, we can unite our strengths to overcome the immense challenges that lie ahead. Progress is fueled by bringing together the most brilliant minds from across the globe. When you reflect on the sheer scale of the universe and the complexity of its workings, you must also recognize the emotional power of these discoveries. Every new insight represents not only a leap in knowledge, but also a profound source of inspiration. It serves as a reminder that while you may be small in the cosmic expanse, it is your curiosity and your relentless drive to understand that make humanity great. How could the magnificence of the universe not inspire you to dream on a grander scale? By delving into the very fabric of the universe, you are prompted to ask, what is the ultimate significance of all this for us? In the end, the secrets of the cosmos are inextricably linked to the secrets of your own being. It is the pursuit of answers to questions that seem impossibly out of reach that propels the human spirit forward. Science and research not only grant you the freedom to dream, but also provide the tools to turn those dreams into reality. The speed of light serves as a profound marker of our current limitations, a constant reminder of how much remains beyond our comprehension. Yet, contemplating ways to overcome this barrier launches us into the exhilarating domain of speculation and discovery. It compels us to ask what cosmic enigmas are still hidden from us, and what future technologies could fundamentally alter our perception of space and time. In this way, gravitational waves are more than a mere physical occurrence. They represent the vast, unsolved mysteries the universe holds. Each breakthrough on this front is another step toward a deeper comprehension of our own place within the grand cosmic scheme. So, the next time you look up at the stars, consider that you are part of a grand journey, one propelled by magnificent questions we have not yet managed to answer. The entire story of our species is, in essence, a history of curiosity. As long as that inquisitive fire continues to burn within us, there is truly no end to what we can accomplish. The crucial question is whether we are prepared to continue this voyage across the boundless ocean of the universe, knowing that the answers we seek depend entirely on our capacity to explore, to question, and to discover.